Not so long ago, scientists used to believe that atoms are the smallest fundamental particles that you can find in any matter, meaning that atoms are indivisible and nothing can exist at the subatomic level. So this experiment, the charge-to-mass ratio of an electron, which was carried out by a British scientist, Joseph John Thomson, just over 100 years ago, it did not only refute that notion that atoms are the fundamental building blocks of matter, but also it showed that at the subatomic level you have the presence of charged particles, and in particular you have the presence of negative charged particles. In other words, the presence of electrons. So that experiment it basically discovered the existence of electrons. In addition, that experiment also showed that if you have a cathode plate is basically a metal plate which is connected to the negative terminal. So when you have a cathode plate and you warm it or you heat it, therefore that cathode plate is going to generate a stream of negatively charged particles. In other words, it is going to generate a stream of electrons. In addition, that experiment also proved that the charge of an electron over the mass of an electron, that ratio E over m, the charge of an electron over the mass of an electron, is basically a constant for any electron of any type of conductor. So whatever the type of conductor that you have, whether it's copper, steel, aluminum, etc., the electrons are always going to have the same charge over mass ratio. So that ratio is going to remain a constant at all times for all electrons of any type of conductor. In addition, that ratio E over m is also a constant for any accelerating voltage applied. So whenever you vary the voltage applied to a material, the electrons are always going to have the same ratio of E over m. So that ratio is going to remain a constant for any accelerating voltage applied. What do we mean by an accelerating voltage? And what would be the relationship in that case between that ratio E over m and the accelerating voltage? Before we start answering these questions and we tackle the theory in depth, we are going to have a basic overview regarding the experimental setup of our experiment of today. If we have a look at the first illustration, we can see that we have two circular coils of the same diameter that are disposed in such a way to be facing each other. Therefore, the combination of these two coils, it forms the Helmholtz coils. So what are the Helmholtz coils? The Helmholtz coils, it's a combination of two coils that have the same diameter and the same number of turns, and that are disposed in such a way to be parallel to each other, to be exactly facing each other. In that case, when you have an electrical current applied to these two coils, you have a magnetic field generated by them. And the majority of the magnetic field generated by these two coils is going to be concentrated at the central region in between these two coils. So if we have a look at the next illustration, we can see that whenever you have an electrical current applied to these two coils, we have a magnetic field generated by them. However, the majority of that magnetic field is basically concentrated at the center. In addition, since we have two identical coils, therefore the magnetic field generated by them is going to be a uniform magnetic field. So when we say uniform magnetic field, we mean that the magnetic field lines are parallel to each other. So as we can see at the central region, we have parallel magnetic field lines, which is an indication of a uniform magnetic field region. However, as we move toward the edges of each coil, we can see that the magnetic field lines, they start to somehow curve, which is an indication that the uniformity of the magnetic field lines near the edges, it starts to drop. So the main point over here, we are using that combination of two coils in order to generate a uniform magnetic field, in order to have a region of a uniform magnetic field at the center in between these two coils. Now let's consider the following sketch, which consists of two circular coils that are identical to the one that we have seen in the previous illustrations. However, at the central region in between these two circular coils, now we have a bulb. So we have actually fixed the bulb at the central region where we have a uniform magnetic field. Now that bulb, it consists of what? That bulb is basically, it's an evacuated bulb which contains a small amount of mercury gas. In that case, the role of the mercury gas inside that bulb would be to render the trajectory of the electrons visible within that bulb. In addition, if we look at one side over here, we have a device which is called the electron gun. So that device over here, we refer to it as the electron gun. So the electron gun, it's basically a device which is going to generate electrons. So that electron gun, it consists of two plates. We have a cathode plate at the bottom, and then at the top we have an anode plate, with the cathode plate being connected to the negative terminal of a power source and the anode plate being connected to the positive terminal of a power source. In addition, that cathode plate is actually equipped with a heater. So right beneath that cathode plate over here we have a heater in order for the cathode plate to generate a stream of electrons. So that cathode plate is going to be equipped with a heater right beneath it in order to render it hot enough. Therefore, the cathode plate would be able to generate a stream of electrons. And therefore, the presence of that power source over here is going to be needed in order to supply the electrons that are generated by the cathode plate with an accelerating voltage so that they can be transmitted from the cathode toward the anode. So over here we are going to have a stream of electrons that are being generated by that cathode plate and directed by that accelerating voltage toward the anode plate. Now the anode is going to be equipped with a special feature. So in the middle of the anode over here we are going to have a small hole. We are going to be piercing the anode in the middle in order to allow for a fraction of the electrons that are generated by the cathode to pass through that hole over here and then to enter into the bulb region. So first off, over here at the apex of that electron gun we have a small opening, and right beneath that small opening we have another opening which is actually pierced through that anode plate. Therefore we are allowing for a small fraction of the electrons that are generated by the cathode to pass through that opening and then to pass through the apex of the electron gun and to enter into that bulb region. So for example over here let's consider that we have the following fraction of the electrons entering into the light bulb at a certain velocity v. Now as we have said before, inside that bulb we have a small amount of mercury gas. So what will be the role of the mercury gas in that case? We said before that the mercury gas is going to render the trajectory of the electrons visible within that bulb. But how can that process actually manifest? So upon entrance of the electrons into that bulb, the electrons are going to collide with the mercury atoms. But we know that the electrons, they are basically carrying an energy, an electrical energy. So upon collision between an electron and the mercury atom, the electron is going to transfer part of its electrical energy toward the mercury atom. Therefore, the mercury atom is initially occupying a ground energy level. So before collision, the mercury atom is basically occupying a ground energy level state. Therefore, upon collision between the atom, the mercury atom and the electron, part of the energy of the electron is going to be absorbed by that mercury atom. Therefore, upon absorption of that energy, now the mercury atom is going to be excited to a higher energy level. So over here the mercury atom is going to be now occupying an excited energy level. However, that excited energy level which is now being occupied by the mercury atom is basically an unstable level, meaning that the mercury atom, it always tends to occupy a lower energy state, a lower energy level. Therefore, instantaneously, that mercury atom is going to drop down the ground energy level. However, while that mercury atom is transitioning from the excited energy level toward the ground energy level, it's going to emit or to re-emit the energy that has previously absorbed. So over here the mercury atom, when it went from the ground energy level to the excited energy level, it absorbed an energy, and in a similar manner when that mercury atom now is going to transition from the excited energy level toward the ground energy level, it's going to re-emit that energy which has previously absorbed. However, it's going to re-emit it in the form of a photon of light. So over here that energy is going to be emitted in the form of a photon of light, meaning that the mercury atom now is going to be emitting a very characteristic light and therefore rendering the trajectory of the electrons visible within that bulb. So that's why over here we place some small amount of mercury gas within that bulb in order to render the trajectory of the electrons visible within that bulb upon their collision with the mercury atoms. So initially, if we don't have any electrical current applied to these two coils, therefore we don't have any magnetic field region in the middle. Therefore, the trajectory of the electron over here is going to remain vertically upward. So the electrons, they are going to enter into that bulb while moving in a vertical upward manner. Now these electrons that are generated by the cathode plate, they are basically located in between a potential difference region. So between the anode and the cathode, we have a potential difference region due to the fact that the anode is connected to the positive terminal and the cathode is connected to the negative terminal of a power source. So these electrons over here that are generated by the cathode, they are located within a certain potential difference region. So due to the presence of the electrons within a potential difference region, therefore these electrons, they possess an electric potential energy stored in them. So due to the presence of the electrons within a potential difference region, therefore these electrons, they are going to be storing a certain electric potential energy in them, and that electric potential energy is given mathematically as E equal to the charge of the electron times the potential difference applied, or times the accelerating voltage. And that potential difference would be the potential difference that is being applied between the anode and the cathode. So you can think of the electric potential energy in a similar manner to how you think of the gravitational potential energy. So the gravitational potential energy is basically a stored energy that arises due to position. And in a similar manner over here, the electric potential energy, it arises due to the presence of charges in a potential difference region. So since we have electrons present or located in a certain region, which is a potential difference region, therefore they actually have a certain electric potential energy stored in them, which is given as E equal to E times V. And that quantity over here, we can also define it as the amount of work done on an electron in order to move it from the cathode toward the anode. Now, what is actually the physical meaning of the electric potential energy? So we know that the electric potential energy is a stored energy. However, that stored energy is ready at any moment to do work, meaning it's ready at any moment to be converted into kinetic energy and therefore supply the charge with enough speed in order to move it from one potential point to another potential point. So that electric potential energy over here is going to be in its totality converted into kinetic energy of the electrons in order to move them from the cathode toward the anode, in order to supply the electrons with enough speed for them to move from the cathode plate toward the anode plate. Therefore, that quantity here is going to be in its totality converted into kinetic energy. And that would be our first equation for today. So we said before that if we don't have any electrical current applied to these two circular coils, therefore we don't have any magnetic field region in the middle, and in that case the trajectory of the electrons is going to remain unaffected. Therefore the electrons are going to enter the bulb region by maintaining a vertical upward trajectory. Now what would happen if we supply these two circular coils with an electrical current? In that case, as we have seen before, in the middle over here we are going to have the presence of a uniform magnetic field. It is going to be concentrated at that central region in between these two coils. So over here we are going to have a uniform magnetic field everywhere in between these two circular coils and right at the central region. Now, since we have an electric charge moving in a magnetic field region, therefore that magnetic field region is going to exert a magnetic force on these moving charges. So these moving charges, they are going to feel the effect of a magnetic force acting on them. And mathematically, that magnetic force is given as following: F equal to QV cross B. And that force, we can also label it as the Lorentz force. So the magnetic force, we can actually label it as the Lorentz force. And it's given mathematically as F equal to the charge times the velocity of that charge across the magnetic field in which that charge is actually moving. So first off, from that equation we can deduce that that magnetic force is actually perpendicular to the plane formed by V and B. Now what we need to do in that case, we need to determine a certain magnitude for F. But moreover, since we are studying the case of moving charges, therefore that charge Q, it can be replaced by E, by the charge E, the charge of an electron. Therefore F is equal to E times the magnitude of V times the magnitude of B times sine theta, which is going to be the angle formed between V and B. So theta is basically the angle formed between V and B. But what would be the angle in that case formed between V and B? So over here we have a stream of electrons being shot vertically upward into that bulb region, and then over here we have a uniform magnetic field, which is basically represented by horizontal parallel magnetic field lines. So in that case, V and B, they are perpendicular to each other. So you have the electron being shot vertically upward, and then you have a region of uniform magnetic field which consists of parallel magnetic field lines or of horizontal magnetic field lines. So V and B, they are perpendicular to each other. Therefore, theta over here is equal to 90 degrees. And in that case, F is equal to EVB times sine 90, and sine 90 is none other but 1. Therefore, F is equal to E times V times V. That would be equation number 2. Now the question is how that magnetic force is going to affect the motion of the electrons, or how the magnetic force is going to be altering the motion of the electrons. So we saw before that magnetic force is actually going to be perpendicular to the plane formed by V and B. So if you have the following stream of electrons moving vertically upward in a uniform magnetic field region, so you have V and B being perpendicular to each other, then in that case you are going to have the magnetic force which is going to act in a way to be perpendicular to the plane formed by V and B. So you have V being perpendicular to B, and then you have that magnetic force being perpendicular to the plane that is formed by V and B. So F is perpendicular to V and F is also perpendicular to B. So how the magnetic force in that case is going to act on these moving electrons? The magnetic force is going to act on these moving electrons by pulling them to one side. So as the electrons keep moving forward, they are going to experience the effect of a force which is acting on them by tilting them to one side. So the trajectory of the electrons is going to be tilted to one side as they are moving forward. So for example, so let's consider over here that we have the following stream of electrons which is moving in a uniform magnetic field region. So over here everywhere we have a uniform magnetic field region. So since we have charges moving in a uniform magnetic field region, therefore they are going to experience the effect of a magnetic force acting on them. However, as we have seen before, that magnetic force is going to be tilting the trajectory of the electrons to one side. So if we carry on with the trajectory of these electrons are going now to be tilted to one side under the effect of the magnetic force. So first off, over here the magnetic force, as we have said before, it's going to act on V and B in a way to be perpendicular to them. You have to imagine that figure in three-dimensional space instead of imagining it in a two-dimensional plane. So you have F being perpendicular to V and being perpendicular to B. So over here, after having the trajectory of the electrons tilted, the magnetic force is going to adjust itself in order to remain always perpendicular to the trajectory of the electrons. In a similar manner, if we carry on with that movement, also we are going to have the trajectory of the electrons tilted to one side, and then in a similar manner over here it's going to be tilted, so on and so forth. So if we carry on with the trajectory of these electrons, as we can see, now the magnetic force is basically forcing the electrons to move along a circular path. However, that magnetic force at each moment is going to adjust itself to remain perpendicular to the trajectory of these electrons. But more specifically, if we look at the direction of that magnetic force is basically directed toward the center of curvature of that circular path of the electrons. So in other words, that magnetic force is a centripetal force. So over here we can deduce that these moving electrons, they are experiencing a magnetic force which is forcing them to move along a circular path, while having the magnetic force acting on them being directed toward the center of curvature at all times. Therefore, that magnetic force is basically a centripetal force. And we have seen before that a centripetal force is basically given by Newton's second law to be F equal to mv squared over r, where m in that case over here is going to be the mass of the electron, r is going to be the radius of orbit. So over here these electrons, they are moving along a circular path at a certain radius of orbit r, so r is going to be the radius of orbit, and finally that velocity over here is going to be none other but the speed of electrons, and that would be equation number 3. So over here we have basically proven that these moving charges, they are going to feel the effect of a magnetic force which is going to tilt them to one side. However, that magnetic force is going to specifically carry these moving electrons along a circular path. It's going to force them to move along a circular path. However, that magnetic force at all times is going to be directed toward the center of curvature. So in other words, that magnetic force is none other but a centripetal force which is given by Newton's second law to be m times v squared over r, and that would be our third equation. So far we have established two equations for the magnetic force. One which is F equal E times V times B, and another one which is mv squared over r. So now what we can do is we can equate equation number 2 to equation number 3. EVB equal to mv squared over r, and that would be equation number 4. So from equation number 4 we can basically deduce a certain expression for the velocity, which is going to be, so v and v squared, we can simplify them. Therefore we have v equal to E times B times r over the mass of the electron, and that would be over here equation number 5. Now taking equation number 5 and plugging it in equation number 1. However, in equation number 1 we don't have v, but rather we have v squared. Therefore we are going to be squaring that equation over here before we plug it in equation number 1. So equation number 5 becomes, after squaring it, e squared times v squared times r squared over me squared. And then we plug that equation in equation number 1. Therefore equation number 1 becomes E times v, so the charge of the electron, times the accelerating voltage, or the potential difference simply, is equal to half the mass of the electron times v squared, which is E squared, v squared, r squared over me squared. So what do we need actually to determine from that equation? We need to determine from that equation the ratio of the charge of an electron over the mass in terms of the accelerating voltage. So we need to establish an equation for E over m as a function of the accelerating voltage. So first off, we can start by simplifying over here the masses. In the numerator we have a certain mass, and in the denominator we have m squared. And in a similar manner over here we have E squared, and over here we have E. So we can start by simplifying these terms. Therefore we have E over m, so the charge of the electron over the mass of the electron is equal to 2 times the accelerating voltage over v squared times r squared. And that would be our final equation for today, which is going to be expressing that ratio of the charge of an electron over the mass of an electron in terms of the accelerating voltage and in terms of the magnetic field that is being generated by these two circular coils, and in terms of the radius of orbit. So over here r would be none other but the radius of orbit of the electrons which are undergoing a circular motion, and b over here is going to be the strength of the magnetic field that is going to be generated by these two circular coils. Now a more detailed explanation for each term, whether for the magnetic field or for the radius of orbit or for the accelerating voltage, is going to be provided in the next video, which is going to cover the experimental parts of the charge to mass ratio of an electron. Now what would happen if the electrons aren't making a 90-degree angle with the magnetic field lines? So we saw before that in order for the electrons to move along a circular path, in order for the magnetic force to drag the electrons along a circular path, the electrons have to be moving at a certain 90-degree angle with respect to the magnetic field lines. So what would happen now if the angle between them, between the trajectory of the electrons and between the magnetic field lines, is not equal to 90 degrees? So let's consider the following example, where we have a uniform region of magnetic field lines in which we have a stream of electrons that is moving at a certain angle theta with respect to these magnetic field lines. So over here we have a stream of electrons moving at a certain velocity v and making a certain arbitrary angle theta with these magnetic field lines. Therefore, that velocity v can be resolved into its two components. It has a horizontal component over here, v parallel, and it has a vertical component, v perpendicular, with v parallel being equal to v cosine theta and v perpendicular equal to v sine theta. Starting with the first component, v parallel. V parallel is basically directed in the same direction of the magnetic field lines. Therefore, that angle theta, which is the angle formed between v parallel and the magnetic field lines, is basically equal to 0. So theta is equal to 0. In that case, the magnetic force F, which is equal to q times v times b times sine theta, is going to be equal to 0, since that angle theta over here is equal to 0, therefore sine 0 is 0. In that case, we don't have any magnetic force acting along the horizontal component of velocity, meaning that that horizontal component of velocity is going to remain moving forward without being affected by any magnetic force, since the magnetic force acting on it is going to be equal to 0. Now regarding the second component, V perpendicular. So V perpendicular over here, which is equal to V sine theta, it's basically making an angle of 90 degrees with that magnetic field line. So theta in that case is equal to pi over 2 or 90 degrees. Therefore, the magnetic force acting on V perpendicular is going to be equal to QVB times sine 90, which is equal to simply QVB. Therefore, over here we have a case which is identical to the previous case that we have studied before. Therefore, that vertical component, V perpendicular, it's going to be moving in a circular manner. It's going to be moving along a circular path. So now we have two components. One which is having a translational motion, and another component which is basically moving along a circular path. So by combining these two motions together, what we are going to obtain is, we are going to obtain a helical path for the trajectory of the electrons. So we have one component which is having a translational motion and another component over here which is moving in a circular path. So by combining these two motions together, we are going to obtain over here a helical path for the trajectory of the electrons.